Here's the video solutions for this acceleration number 4. So you should have your kinematics equations notes. If you're looking at that and you're like, whoa, what's that? That means you probably have not done that yet. So you need to watch that 20-minute video first and have this information very close by to you. Alright, so let's see what we need to do here. So I'm going to follow these little step-by-step instructions here. It's on the first page here. I'm going to make a diagram, and then the table, that's the list in the example problem I did in the notes video for you. That's this list of values right here. Right, we're going to make that little list, and then I'm going to write the equation that I need from this list. I'm going to write it down without putting any numbers in yet. And then I'm going to put the values in, and then I'm going to do some algebra and find the answer. All right, I'm going to do them in that order, do all the steps just like that every single time. So number 1, got a little shopping cart, runaway shopping cart. It's not hard to imagine around here. If you've ever been in the Kroger parking lot, that can happen. Starting from rest, so from rest means that its initial velocity is 0, and it accelerates down a hill. There's Kroger down here at the bottom of the hill, and at a constant rate of 0.9 meters per second per second. So giving us the acceleration. Sometimes I've had students in the past who kind of struggle with knowing like what number is what. So the units, remember the units are going to help you figure out, direct you toward the right thing. So this is meters per second squared, or meters per second per second. So that must be the acceleration. All right, and then we want to know how fast is it traveling after 5 seconds. That's part A. Okay, so let's make our list. I'm going to try to write these down in the same order every time to be real consistent. It doesn't really matter what order you put them in, but I think consistency is good. So what do we know? I know my initial velocity is 0. I know my acceleration is 0.9 meters per second squared. I know my time is 5 seconds, and I would like to know in part A how fast is it traveling after 5 seconds. That's the final velocity. So that's the thing that I'm not using right now. So look at my equations. The one that's missing delta x is this. So go ahead and copy that down. In the notes, I wrote that down as VI plus AT. I think more commonly I write it down, and you'll probably see it more written like this. Of course, addition is commutative, so it doesn't matter. 2 plus 3 and 3 plus 2. Same thing. So VF is equal to, put my numbers in now, 0.9 times 5 plus 0. That's 4.5 meters per second. Great. And then for B, I don't think I need to redo all that. How far has the cart traveled? So that'd be looking for delta x instead. So if I was looking for delta x and didn't have this, of course I do have it now, but if I was doing that first, that'd be the equation that was missing VF. That would be this one. So I'll go ahead and write that equation down. And then I'll write it down again with the things plugged in that I know. What's 0 times anything? That's 0. So looks like my delta x is going to be 11.25 meters. Great. How did I know the units would be meters? Well, I'm finding a displacement. So if everything's in SI units, which it is, then that will be meters. All right, that's how you do it, folks. Number 2, I got a bicyclist. It's really up to you how artistic or not you get. Oh, that's not a very good bicycle. I don't really know how to draw a bicycle very well. Well, there you go. It's traveling at 12 meters per second. When she applies the brakes, the bicycle slows down at the constant rate of negative 3.75 meters per second. Even it doesn't say acceleration anywhere there, but I know that that's the acceleration because of the units and the rate that the velocity is changing at. That's what acceleration is. All right. There's a little note there about signs. I think we're good. If she's going this way and that's positive, then the acceleration, she's slowing down, the acceleration would have to be negative. It's like subtracting away from the velocity. How long does it take for the bicycle to come to a complete stop? So remember, if we're coming to a stop, that would be a final velocity of 0 there. Okay? And how long is asking about that time. So I'm going to make my list. And I'm going to fill in what I know here. Looks like I'm looking for the time here. So I don't know that right now. So I'm looking for the equation that's missing delta x. And you have your notes there. I don't need to keep flashing that paper at you. That's this one. There it is. And now here it is again with the quantities that I know plugged in. I like to leave the units off when I'm doing my algebra, because it just makes the equations cleaner. I feel like it can be a little confusing otherwise. So you know how to do algebra. I don't know. You one of those people that likes to make algebra mistakes? Got to be careful. There is math involved here. All right, so 3.2 seconds it takes her to stop. And then for part B, the question for part B is how far? Well, that's the only other thing that we don't know yet. That's that delta x. And if I wanted to use all of these things, that would be the equation that's missing time. There's the equation. I'm going to write it down again with the stuff plugged in. And algebra happens, and you end up with (19.2 meters. Make sure you can do that algebra successfully, please. All right, number 3. A car is traveling 9 meters per second and it begins accelerating at a constant rate. So we're going 9 meters per second, and then it's going to accelerate for a little while. That's the same car, I promise. And it's going to be going 24 meters per second. All right, and that takes 6 seconds. this would be the initial velocity, and this would be the final velocity. All right? And part A, we want to know what the acceleration is. So let's see what we know. This is 9. This is 24. And looking for the acceleration right now. So that's the equation that's missing, delta x. That's this one. So I'm writing that as 6t instead of, oh yeah, that's, no, sorry, 6a. I'm switching the order of those because that jives better with what I'm used to doing algebra, right? Like a6, that's kind of weird. We would write that as 6a. So I subtract the 9 and then divide. You get the acceleration is 2.5 meters per second squared. And then for part B, looking for the other thing. So let's see, let's pretend we didn't know that. What's the equation that has these things in it? That is the delta x is equal to 1/2 vi plus vf times t. So delta x all that. So I think that's 99 meters. If you do the math there. Right. Great. Number 4. On the runway, an airplane starts from rest. Oh dear, let's see. Airplane. A tail, and then this part, and then there's like a wing coming off like that. All right. That's not terrible. It starts from rest. I'm not going to take off any points for you not being able to draw an airplane, in case you're worried about that. And begins accelerating at a constant rate. They're not telling us what that is, though. After traveling a distance of 960 meters, the airplane takes off. Oh, I'm assuming that it takes off. Maybe it does. Who knows? And the final velocity there is 110 meters per second. And what's the average velocity of the airplane over the 960 meters? How do you find average velocity? That's displacement over time. It doesn't matter whether you have acceleration that's constant or no acceleration or variable acceleration. This is always what average velocity is. It's always change in position, or in other words, displacement divided by time. So let's see what we know. I feel like I don't have enough information. I feel like this question is asked maybe in the wrong order, because I know what the displacement is, right? That's 960. I could just write that in. But I don't know what the time is yet. And part B is how much time does it take. So I think that right off the bat, maybe we just want to find the time. And there is another way to do that too. I'll come back and tell you in a second. So let's make our list. And see what we know. The delta x so if we want to know the time, delta x is equal to the So it looks like we have 960 divided by 55. So that's the time, and now that we have that, we can bring that up here. Do 960 divided by that. And that gets me 55 meters per second. Now, I do want to point out something to you here. You might notice, maybe not, that if you took 0 and 110 and averaged them, add them together, divide by 2, you get 55. So in fact, we could have done that part A, but we just need to recognize that if the velocity is changing at a constant rate, the average velocity will be the average of the starting and ending velocities. So either way you want to do that, set that up, is fine. I bet we're going to be asked for the acceleration here. Yep. What's the rate of acceleration? So let's pretend we didn't know that. That looks like that equation there, and with numbers plugged in, oops, sorry, that's the 960. Right, so 110 squared divided by 2 times 960. If you're entering this into your calculator, just make sure that when you divide that you're dividing with that in parentheses. If you don't put the parentheses there, you're like, it doesn't matter, don't need those parentheses. You do, because that's a completely different number. Whoa, what happened there? Well, the calculator thinks here that you mean do this number, divide by 2, and then multiply that by 960. Like, it has no way of knowing that you meant for that to be on the bottom. Here's the safest option. If you go to your F1 alpha, go to the little F1 there, and pick up that little number 1, that fraction thing, then you can enter it as just how it looks. And then you don't have to worry about the parentheses because you can see that both of those are on the bottom. So just be careful with your calculator management. 5, student rolls a bowling ball down a hill. This doesn't sound like a good idea. You think it's the Kroger parking lot again? With an initial velocity of 2.4 meters per second. After traveling a distance of 8 meters, the ball, those little lines mean it's going fast. Now the ball is going 7.2 meters per second. What's the average velocity of the ball? Want to take the shortcut this time? Now, since we talked about that, it's just the average of those. So average velocity is the average of the velocities of the starting and ending velocity, and that would be 4.8 if you do the math there. You could also do it like we did here. You could find the time first. Let's see, how did we find the time? Well, actually, now that we know, I could also use this equation. You can do the same thing that we did here. That is an option. We've got a lot of different equations we can use. As long as you can make one work for you, it is good. So average velocity we just found is 4.8. Delta x I know is 8 over time. So this might be a little bit easier way to get that time. And then doing algebra, that pops up there, that goes down there. So 8 divided by 4.8 is about 1.67 seconds. And then part C, what's the acceleration? So we could do the same thing that we did here. Really, pretty much the identical problem to number 4. So my VF squared is 7.2. I'm setting a bad example here. I didn't write out my list, and I said I would do that every time, and I apologize for not doing that. You really should do that every time. All right, I think that's all good there. So, time to do some math. I get about 2.88 meters per second squared. All right, number 6. Another car. Initially moving at a speed of 9 meters per second, enters a highway and accelerates 4 meters per second. How fast will the car be moving after it has gone 56 meters? Maybe that's like the length of the ramp or something. All right, what is this? I mean, maybe pause just for a second to think about what this means. So if you're going 9 meters per second and your acceleration is 4 meters per second, how fast will you be going 1 second later? Well, this acceleration, it tells you what's happening to the velocity every second. This means that the velocity is increasing by 4 meters per second every second. So 1 second after this, you would have to add 4 to this. It'd be going 13. And then another second after that, 17, and 21, and so on and so on. Adding 4 every second goes up. How about only how? It doesn't go up like in blocks of 4. It goes up continuously so that at the end of every second you have added 4. So if you did half a second, you'd add 2, right? And so on. All right, what do we need here? How fast will the car be moving after it has traveled 56 meters? No parts in this one, just one question. So I'm going to make my list. And we're looking for how fast will it be going. So that's this. So I don't need that. The equation that is missing time is this one again. So VF squared, I'm looking for the VF, don't know that yet. So do all that and then take the square root of it. All right. Last one. Truck having an initial speed of 16 meters per second. Oh, that's good. It has an initial speed of 16. It's slowing down. So if it has a positive velocity and it's slowing down, then I don't know the acceleration, but it's better be a negative number. It's going to slow down for 4 seconds, and after 4 seconds, it has a velocity of 6. This is going faster, and then over here, it's going slower. See, it slowed down. All right, so we want to know how far does it go. So that's the how far. Don't need that. That looks like this equation here. And that is all we need to do. All right, that's how you use the kinematics equations.